Okay, so guys, yesterday we have studied about the static routing, and in static routing we have manually mentioned the unknown network to the routers. So if this network is something like 30.0.0.0 and this is 40.0.0.0, then we will define it manually in the routers. That's what static routing is. Now dynamic routing, talking about the dynamic routing, I told you in dynamic routing we will use some protocols. We'll use some protocols. Now, these protocols are of two types. The first is called interior routing protocol. Okay, so what we use is called routing protocol. In dynamic routing, what we use is called routing protocol. Okay, with routing protocol, say we will share the routes, and we have two routing protocols: interior routing protocol, exterior routing protocol. Interior routing protocol and exterior routing protocol. Now, interior routing protocol is used to share the routes between the same organization. Okay, which is interior to the organization. Okay, now exterior,
Like land.
like, yeah, multiple LAN. Okay, now that suppose, okay, so previously, or say in the example that I told you yesterday, we had two branches, the Delhi branch and the Bangalore branch. So the Delhi branch will be having LAN, multiple LAN they may have. Okay, and the Bangalore branch also, suppose they have multiple LAN. So these LAN information can be shared between these routers of the same organization. Yes,
I got a problem over here. Just
what happened?
I got this message. This is right or wrong?
Just give me a minute, guys. Yes, guys. So we were talking about the interior routing protocols and the exterior. So interior routing protocols means we will share the routes. Okay. So which is, say here, the Delhi route or the Delhi branch has got multiple routes here. Okay, and the Bangalore branch will have multiple routes here. So between the same organization we are sharing the routes. Okay, so to share the routes between the same organization we'll use the interior routing protocols. And to share between different organization, then you can use this exterior routing protocol. One such example is BGP. One example for the exterior, the only example for the exterior routing protocol is BGP. Okay, now for interior routing protocols you have many protocols here. We will study one. Okay, so RIP is an example of an interior routing protocol, routing information protocol. Then the next one, Eigrp, is another example for, say, interior routing protocol. And Ospf is next example for interior routing protocol. So you got many interior routing protocols. Okay, now we'll be studying about the interior routing protocols, RIP, Eigrp theoretically, and Ospf will do it. Okay, now talking about RIP. Routing information protocol. Routing information protocol, RIP. Shall we?
Yes.
Now this is an open standard protocol. It's an open standard. Okay, Now, RIP comes under the family of distance vector protocol. It comes under the family of distance vector protocol. Okay. Now, RIP here, it uses an algorithm called Bellman-Ford algorithm. Bellman-Ford algorithm. And now, let me just tell you about it. Say here, we got routers R1, and suppose this is R2, and we got networks here. Okay, suppose this is 20.0.0.0/30, and this is 10.0.0.0/24, and I suppose yesterday I've given 30.0.0.0/25. Okay, now to share the route, so here by default R1 will be having 10.0.0.0/24 in the routing table. It is directly connected. Okay, now so again it also has 20.0.0.0/30 network, which is also directly connected. Now again with respect to R2, when we talk about R2, so again R2 consists of a routing table, and the R2's routing table will be like this. So directly connected 20.0.0.0/30 and directly connected 30.0.0.0/25. Okay, now if you implement the or if you say execute the protocol RIP, or if you do the protocol RIP here, what happens is that RIP will keep on sending updates. RIP will keep on sending updates. So he will send the update like this: hey router, hey next router, I know about two networks. I know about 10.0.0.0 network and 20.0.0.0 network. Like that he will send it. Okay, so he will send the updates, and the updates will be sent periodically. It will be sent periodically. That means it will be sent for every 30 seconds. It will be sent for every 30 seconds. Okay, so the periodic updates are sent for every 30 seconds in RIP. Now R2 also shares the same thing. R2 also shares like this. Say I've got a network which is 20.0.0.0/30 and 30.0.0.0/25. Clear? He'll keep on sharing for every 30 seconds. Okay, now the next thing. So now RIP uses a value called hop count. RIP uses a value called hop count. So now let me tell you what is hop count. So hop count means the number of routers it has to pass. To reach a network, how many number of routers it has to pass, that is called the hop count. So for R1 to reach the 10 dot network, it doesn't have to go to any other router because it is directly connected. So the hop count is 0. Okay, now so here for 20 dot network, the hop count is here also, the hop count is 0 because it is directly connected. Now again for here the hop count. Here also for R2 to go to 20 dot network, the hop count is 0. For R2 to go to 30 dot network also, the hop count is 0. Clear? Now when R1 shares its routing table, or when R1 shares its known routes to R2, I told you R1 will share the 10 dot network and 20 dot network to R2. So when R1 shares it to R2, R2 already knows about the 20 dot network. He's going to ignore it because he already knows it. Now about the 10 dot network. So 10 dot network will be then placed in the routing table, 10.0.0.0/24. It will be placed in the routing table. It will be placed in the routing table, and you can see an alphabet R, which corresponds to RIP, routing information protocol. Okay, now here this time the hop count will become 1. The router 2 will increase or will increment 1 hop count. Because for R1 to reach 10 dot network, the hop count is 0. For R2 to reach the 10 dot network, it has to go to R1. That means one hop is to be made. After that, it will reach, or it can go to 10 dot. So the hop count will be 1 here. Clear? Okay. Now again, the same thing happens between say R2. So when R2 sends the 30 dot network, say R1, what he will do is that he'll update that in the routing table 30.000/25, and the hop count will be 1. Clear? Okay. So this is how they will send the routes. Any doubt? Okay. Now one more thing. So let me just tell you about one more thing here. So this hop count, this value is called metric. This value is called metric. We got a common term called metric. If I ask you, say, usually I'll go with an example. Okay, now that I ask you, which is your favorite bike? To suppose Kevin. Okay, Kevin will say, suppose here his favorite bike is supposed to say Royal Enfield Bullet or whatever it is. Okay, and say this is his favorite bike, and he has a specific reason to buy that bike, right? Say suppose it is of the brand that he likes it, Royal Enfield brand. Okay, brand. Now if I ask Srikanth, then Srikanth will tell, suppose he likes suppose Triumph. Okay, he likes Triumph. So because say it is having more power or whatever, again, so he has got another say choice there. Okay, so here each protocol will have, or they will have their own value here, or they will consider one thing as the value. Okay, and based on the value it will work, and commonly we call them as metric. Commonly we call them as metric. So RIP uses a metric of hop count, you can see. RIP uses a metric of hop count. Clear? Now talking more about the RIP. So talking more about the RIP, let me tell you some more thing. RIP will support maximum up to 15 hop count. RIP supports maximum up to how many hop count? 15 hop count. If the hop count is greater than 15, then that is, the network is considered unreachable. The network is considered unreachable. Clear? Okay. Now here RIP has got two versions. RIP has got two versions, RIP version 1 and RIP version 2. And in RIP version 1, let me tell you about the RIP version 1 here. It doesn't support classless address. It doesn't support VLSM. It doesn't support authentication, etc. But RIP version 2 supports everything: classless, VLSM, authentication, and everything. Okay. Okay. Now, one more thing. Now one more thing. So RIP version 1, so I told you that it will be sending the periodic update. For every 30 seconds he'll be sending the periodic update. So when you send something, that will be having the source IP and the destination IP. The source IP will be its own interface IP, the sender's its own interface IP, and the destination IP for RIP version 1. The destination IP of the updates for RIP version 1, that is the universal broadcast address 255.255.255.255. Okay, while for RIP version 2, the destination IP is 224.0.0.9. It's a multicast address. Okay, please note it down.
Bharat, is this broadcast ID or what? 255, 255 and 224.0.0. Hello, can you hear me?
So guys, anyone ask a question? Yes, Nikhil?
Yeah, can you hear me?
Yes, Nikhil.
Yeah. So I was asking, what are these? Is this broadcast IDs?
Sorry?
The IPs that you have written, is this a broadcast ID? What is this?
Yes, of course it is a broadcast IP. So for the RIP version 1, they will use the broadcast address to send the updates. Okay. And for RIP version 2, they will use a multicast address called 224.0.0.9 to send the updates.
Okay.
Okay. Yes. It's just nothing. It's just that they are sending the routes. Okay. And while sending the routes in the IP header, you will have the destination IP as 255.255.255.255. Okay, and there's actually a problem while sending this as with the destination IP as 255.255.255.255, because say whoever receives this message, say it's a broadcast, so whoever reads the message will be accepting it in layer 3. Okay, whereas say for 224.0.0.9, it's reserved for RIP. Okay, RIP version 2. So those who are not running RIP, if they receive these packets also, they will not read it, because that is not meant for them. It is meant for the routers participating in RIP. Clear? Okay. Now, fine, Nikhil. Okay.
Yes.
Okay. Now guys, so this is the RIP, routing information protocol. Okay. Now we'll come to another protocol called Eigrp. Okay. So you can write the next heading, Eigrp, which means enhanced interior gateway routing protocol. Gateway routing protocol. Enhanced interior gateway routing protocol. Okay, let me tell you about Eigrp. So Eigrp, it's a Cisco proprietary protocol. I can say it was a Cisco proprietary protocol. Okay, Cisco has developed this protocol Eigrp. Previously they have developed something called IGRP, and this is the enhanced version of IGRP protocol. And what Cisco did was, for some time Cisco, say they had this protocol as its own proprietary protocol, and nobody else was allowed to use. That means no company was, or no other vendors were allowed to use this Eigrp. Okay. Now what they have done is they have made it public in the sense the copyrights and everything still remains with the Cisco, but it can be implemented in all the routers. Okay, so it was Cisco proprietary, but now that say they have made it public. Okay, now again Eigrp, it works, or it comes under the family of advanced distance vector protocol. It comes under the family of advanced distance vector protocol, or it's also called hybrid protocol. It's also called hybrid protocol. Advanced distance vector protocol or hybrid protocol. Okay, now the next one. Eigrp uses an algorithm called dual diffusing update algorithm. Diffusing update algorithm. Okay. Now again, Eigrp, again I told you about the metric value. So Eigrp will calculate the metric value based on certain parameters. So you can write Eigrp will calculate the metric value. Eigrp will calculate the metric value based on certain parameters. Called K values. K values. Okay. Now, so I told you that say Eigrp will calculate the metric using some parameters called K values. So there are certain parameters which are used to calculate the metric. So the parameters are K1, which is bandwidth, K2, which is load, K3 delay, K4 reliability, and K5 MTU. Bandwidth, load, delay, reliability, and MTU.
Last one is MTV.
MTU, maximum transmission unit. Okay. Now, nowadays you do not use say MTU to calculate the metric. So now you can use K1 to K4 to calculate the metric, and by default Eigrp uses only K1 and K3 value by default. Okay, to calculate the metric they will use the bandwidth and delay, while you can configure Eigrp in such a way that they can use all the four values to calculate the metric. Clear? Okay. Yeah, it's similar to like this. Okay, suppose that I say Kevin wants to take a bike. The same example, Royal Enfield. He is choosing Royal Enfield. Why? Because he considers many factors. Okay, he considers power. Okay, or suppose some other example other than Royal Enfield.
BMW.
Yeah, BMW maybe. Okay, so BMW say it has got enough power. Okay, and it's like what do you say? It's a status that owning a BMW bike, right? So nowadays you can own BMW for 2 lakhs, I suppose, 2 or 4 lakhs. Yeah. So owning the BMW, it's a brand. Okay, it's a brand value. The brand value is there. Okay, and of course say you got what's it? Yeah, Kawasaki, and so not Kawasaki, but BMW.
Honda Highness.
Sorry.
Honda Highness.
Honda, okay, whatever it is. Okay, so Honda Highness or BMW also, I was just telling you that say it has got power, the brand value. So Kevin will consider everything here. Okay, he'll consider again money. So of course within 4 lakhs when you get a BMW you will go for that only, right? Okay, then say suppose it has got the suspension quality is good, suppose. Okay, then and many factors. So Kevin will consider all the factors and then will buy this bike. Okay, so same with the Eigrp say it takes many values into consideration and then it will choose the best path. Clear? Whereas say only based on the hop count the RIP chooses the best path. Okay, and again I forgot to tell you, suppose in case of RIP, if you use RIP here, suppose you got R1, R2, suppose R3 and R4. and R4 has got a network here which is 10.0.0.0/24, suppose. Where is it? Yes, /24. Now for R1 to reach this 10 dot network, how many will be the hop count, or what will be the hop count? 2, 3. Okay, let me tell you. So for R1 to reach R4, 1, 2, 3. 3 is the hop count. Or you can check the reverse as well. So whenever R4 sends the route, R4 will send the route like this. R4 will send it to R3, and R3 will increment the hop count, and the hop count will become 1. For R3 the hop count will become 1. Then R3 will send the route to R2. Okay, and this time R2 will increment 1, so the hop count will become 2. Then again R2 will give it to R1. Okay, and R1 will increment the hop count, and the hop count will become 3. So finally the hop count is 3 for R1. For R1 to reach the 10 dot network, the hop count is 3. Okay, now what if you have another value, say R6, R7, and say this connection? Then R1 has got 2 paths. R1 has got 2 paths to reach the 10 dot network. Both are having the hop count of 3. So this is 1, 2, and 3 here. The same thing. Say 1, 2, and 3. Okay. So if both the paths are having the same hop count or the same metric, then load balancing will happen. What will happen? Load balancing will happen. Okay. That is called equal cost load balancing. Equal cost load balancing. Clear? In case of equal metric or in case of equal cost, the load will be balanced. Clear? Now again let me tell you one more thing. Suppose you got another router in between here. Here in between you got another router R8. Then the hop count here will be 4. 1, 2, 3, 4 will be the hop count. And this time the hop count will be 1, 2, 3. 3 will be the hop count. So the router will be choosing the path with the least metric value, or the least path the least hop count. Okay, so that means R1 will choose the upper path to reach the 10 dot network. Clear? Okay, so these are the things. And now so RIP actually it only takes say the hop count into consideration. He will not take any other values. Suppose that here you got a better path. Say suppose the hop count is 4. Of course the RIP will not choose this path. But what if the bandwidth is high? Suppose the bandwidth is 10 Mbps here. Again here it is 10 Mbps. Here again it is 10 Mbps. And suppose it is 1.5 Mbps. Here also 1.5. But still the RIP will choose only the upper path. Getting it? So Eigrp is not like that. Eigrp will choose the best path based on multiple parameters. Getting it? They use an equation and all, and will calculate the metric value, and then will choose the best path. Now again one more thing about Eigrp. Eigrp, it maintains 3 tables. It maintains 3 tables. The first table is called neighbor table. It's called neighbor table. Okay. The second table is called topology table. And the third table is called routing table. Neighbor table, topology table, routing table. Okay, now let me tell you about these tables. So suppose you got 2 routers here running in Eigrp, R1 and R2. Okay, suppose they got 2 networks, and here it is, say, or let the diagram be like this. R1, now R2. Suppose you got a link here, and this is 10.0.0.0/24, and this is 30.0.0.0/25. Okay, now suppose you got another route, R3. and you got one more route here. Okay, now so this is R4, R5, R6, R7 and R8. Okay, now what happens is that these routers will send hello packets to each other. Okay, these routers will send certain packets called hello packets. Okay, now give me a minute. Yes, so now the routers, when configured with Eigrp, so we are now talking about these two routers only. Okay, so what happens is that they'll send certain hello packets. Okay, say hello, they'll send certain packets, and when this router receives the hello packet, and they will cross check it, they'll cross check whether some parameters matches or not, then or some conditions satisfy or not. If certain conditions satisfy, he will also send a hello packet, and you will tell that between R1 and R2 the neighborship will be formed. What will form? Between R1 and R2 neighborship will be formed. Okay, suppose we got Srikanth here, and we got Kevin here. So Srikanth, he is telling hi to Kevin. So Kevin will look at him and check whether, say, certain conditions satisfy or not. If certain conditions satisfy, he is gonna send hello, and then they will form friendship. A formal friendship is formed. The same thing here. Say they are gonna send certain hello packets between each other, and if certain conditions satisfy, they'll form neighborship. Okay, and if the neighborship is formed, they will update it in the neighbor table. R1's neighbor table will have R2's information, and R2's neighbor table will have R1's information, because they have just become neighbors. Okay, now what they will do is that they will start sharing the routes. R1 will share the routes to R2. R1 will share, hey R2, I know about the 10 dot network. Then R2 will also share its routes. I know about 30 dot network. Getting it? Now, these routes will be saved in the topology table, or in the topology table you will have possible route information. You will have what? You will have possible route information. Clear? Now, again say, so R1 receives the 30 dot network from R2. It will be saved in the topology table. Now, R1, so R2 will send this information to R3, R2 will send the information to R8, R8 will send it to R7, R6, R5, R4, then to R1. So for R1 to reach 30 dot network, it has got 3 paths. Are you feeling confused with the diagram or something? Okay, fine. So for R1 to reach 30 dot network, it has got 3 paths. Okay, so now consider the topmost path. It is not a possible path. It's not a possible path. Then that will not be included in the topology table. Okay, now that you got 2 possible paths, the middle one, this one, and the lower one, downward one, which will be there in the topology table. Then the Eigrp routers will calculate the metric and place the best route in the routing table. Clear? So the neighbor table contains neighbor routers information, the topology table contains possible route information, and the routing table contains best route information. Clear? So this is how Eigrp will work. Getting it, guys? Everyone fine? Okay. Now if you ask me which is the better protocol, so if we consider RIP, Ospf and Eigrp, if you ask me which is the better protocol, I would tell you the better protocol is Eigrp, because of many factors. The first factor you already know, Eigrp takes many values to consideration. To calculate the metric, they will use many values. They'll use bandwidth and delay by default, and they can be configured to use the reliability and also the load to calculate the metric. Okay. Eigrp uses multiple parameters to calculate the metric. That is one thing. The second thing is that Eigrp has, okay, it has, just a minute. Okay, so it has got the possible route information. The possible route information in the topology table. That means, sorry, it has the best route in the routing table and the secondary route. If at all the best route is going down, consider the best route is in the routing table. Say if at all the best route is going down, the next best route or the backup route is already there in the topology table. He has already found out the best route, okay, or the second best route. So he can directly place that it in the routing table. If at all the best route goes down, he can place the second best route directly in the in the routing table without calculating anything. Getting it? Okay, just nothing. Suppose, say Kevin wants to go to, say, Bangalore railway station or Bangalore airport. Okay, he knows one route. What if that route is blocked? If the, say, suppose the authorities have blocked it, he knows another path. So already he saved in his mind, he has saved the another path in his mind. So he can go via another path. The same thing. Eigrp stores, I told you, the possible route in the topology table. Okay, so the possible route is there. That means the secondary path is also there. Say in this figure, I told you, where is the figure? Yes, in this figure I told you, so the first path and the secondary path, say those are the possible route and they'll be saved in the topology table. Right, so if at all the best path, suppose the lower path is the best path, if it goes down, it still can use the upper path, I mean the middle path. Getting it, guys? Okay, so that is one more thing. And again one more thing. Okay, Eigrp supports unequal coast load balancing. Unequal coast load balancing. Okay, means suppose, so previously I told you in the case of RIP, I told you if you have, say, or if you have a topology like this, here you got 10.0.0 network and here you got another network here. Okay, so the path, sorry, this path contains, the hop count will be 3 for the upper path, and the lower path also the hop count is 3. So if both the, say, the metric value are 3 or the hop count is 3, or when both the value hop count are same, then you can load balance. But if the hop count is 4 here, you cannot load balance. Similarly, Eigrp supports equal coast load balancing. That means if suppose the metric is 200 here, for the first path the metric is 200, and for the second path the metric is 200. If both the path you have the same metric, then that will load balance. Okay, now if it is 201 or 210, it is unequal coast load, right? Or say unequal coast or unequal metric. Then you expect Eigrp to send the package via the lower path. The least metric path will be chosen. Getting it, guys? But Eigrp can still be configured. So Eigrp will go with the least metric path only, the path with the least metric value. But still it can be configured in such a way that they will do the load balancing even if you have, say, multiple metric. Getting it? Or say different metric value. Clear? So that is also one thing. And one more thing, let me tell you, Eigrp, what is the AD value of Eigrp? Administrative distance value. AD value. I suppose I taught you on Friday, right? What is AD value, administrative distance? What is it? What is AD value, guys? Revise. It's not when I ask the questions that you need to revise. Not written. Are you sure you're not written? AD, administrative distance. I remember.
Administrative distance is a value that router will choose the lesser one to comparing to multiple routes to take the best one.
50.
What you told is true, yes, correct. But here the AD value is not correct. The explanation he told is correct. Okay, let me tell you. Suppose, let me tell you with an example here. Now, so Kevin, this is Kevin. So he is in Bangalore. He wants to go to, suppose, where? Delhi. He wants to go to Delhi. Okay. So this is Delhi, or this is a place, whatever it is. So he wants to go to Delhi. Now, he will ask many person how to go to Delhi. Okay. Suppose he will ask Nishant. He will ask Srikant. He will ask Ritik, right? Okay. And he'll ask maybe me. Now he'll ask or suppose, let me now consider different values. Say here he has asked Nishant. Okay. And now he has asked his roommate. Suppose he is staying in a PG and he has asked his roommate. Okay, PG roommate. Now he has asked his brother. His brother. Now he has asked a shopkeeper. Shopkeeper. And suppose he has asked conductor also, the bus conductor, or say suppose the driver. How I can go? Through which bus I can go? Each will have their own opinion. The driver will tell, hey, both this bus I'll take you to Delhi, or this bus will go to Delhi. Shopkeeper tells him, so the driver tells, take that bus, take the bus. The shopkeeper tells him to walk from Bangalore to Delhi, he need to walk. Okay. Nishant tells, you can take train. Okay. Now roommate, he tells, you can say go via, you can take boat. I don't know how you will go via boat, but suppose roommate told you can go via boat. Okay. Now his brother tells him, okay, you can take flight. Okay. Now, so different people is telling different path. Okay. Suppose, let me just tell you with the technical example now. So suppose this is our router R1 or Kevin. Okay, wants to go to Delhi or 10.0.0.0/24 network. Okay, now just he has got how many paths? 4 paths now. 4. 1, 2, 3, 4. Okay, he has got 4 paths. So now, if you use RIP, routing information protocol, which path will RIP tell you to go? The first path, the second path, third path, or the fourth path? Yes, guys? Second. RIP will tell you to go via the second path because of the least hop count. Getting it? So the hop count here will be 1 only. But if you go via this path, the upper path, the hop count will be 2. If you go via the lower path also, the hop count will be 2. And if you go via the lowermost path, the hop count will be 3. Okay. So RIP tells you to go via this path. Okay, the second path. Suppose you have implemented Ospf. Ospf tells you to go via this path, the first path. Okay. Now, say you have implemented Eigrp. Eigrp is telling you to go via the third path. Okay. Now, the static route. You have implemented the static route. So the static route says the packet should be forwarded here. If at all you got multiple protocols telling you about the same network, that is where AD or administrative distance is used. Okay, that means here say the same, say let me take this the previous example here. The shopkeeper is telling him to go, or he is telling him to walk from here to Bangalore, to Delhi. Okay, and the driver is telling to take the bus to Delhi. To reach Delhi, they are telling, each person is telling different method. Okay, so the same thing here. To go to the 10 dot network, each protocol is telling different path. To sort out which path is the best among all these one, we will use a value called administrative distance. Clear? So the Ospf has got an AD value of 110. The RIP has got an AD value of 120. Eigrp has got an AD value of 90, and the static has got an AD value of 1. So the router will consider the path which has the least AD value, which is 1. That means the router will be sending the packet towards this router only. Getting it, guys? So AD value or the administrative value, it's actually a number. Okay, it's a number that ranges from say 0 to 255. Okay, and it is used to select the best path when the route is advertised by multiple routing protocols or multiple routing domains. When the same route is advertised by multiple routing protocols or multiple routing domains. Clear, guys? Any doubt? Paka, everyone? Okay, now so Kevin has sorted out. Okay, suppose say again this AD value. So here say driver, say he will not consider it. The driver has 100 points, he will not consider. Shopkeeper has 20 points or say 200 points, he will not consider. Nishant has got say 10 points. PG has got PG mate has got 50 points, and brother has got 1 point. Okay, so that means whatever the brother says, he will be taking that path only. Getting it? Now, what if he asks his brother? Brother says you can go via flight. Now, he asked his dad. Dad says you can go via train. Now, he asked his mom. Mom told you can drive and go. Okay, I don't think mom will tell you like that, but still. Okay, you can drive and go, or you can take the car and go. Okay, so within the family itself, say you got different opinion. Within the family itself, you got different opinion. That means within the family, in the sense here in this case, suppose that say you are using a single protocol here. You are using the single protocol RIP. If you are using the single protocol here, again they will come with them, or they will choose the best path based on the metric value. Okay, if you use only the same protocol, then they will check the best, or they will select the best value or the best path using this metric. Getting it, guys? So this time the AD value is not taken. Okay, because the AD value is already sorted out. Okay, suppose that here in the previous example, so here, just give me a moment. Yes, in the previous example, say I have used Eigrp instead of static. I have used Eigrp, RIP and Ospf. Okay, then different protocols are there, then they will go with the Eigrp because Eigrp is having the lesser AD value. Now if I use the Eigrp completely, here if I use Eigrp completely, then say suppose it says the metric is 100. If you go via this path, the metric is 100. If you go via this path, the metric is 200. If you go via this path, the metric is 50. And if you go via this path, the metric is 80 or 800. Then the metric will be, so the least metric path will be chosen. Do you need any more explanation? Everyone clear? Ritik also? Okay. Online guys? Clear with this concept?
Yes, sir. Yes.
Yes, sir.
Okay. So this is how, say, they will send the packets. Okay. Now, so, and yes, I was telling you about the AD value, and what is the reason that, yeah. So, EAGRP supports unequal coast load balancing also. That is another reason for EAGRP to become good protocol. Okay. And again, AD value of EAGRP is lesser. It has got an AD value of 90 only. Okay. So EAGRP will be considered as the, say, when you compare EAGRP with OSPF and RIP, EAGRP is the better one. Okay. Yes. Now, shall we go with the next one, or need a break? Anything? Need a break or something? Then we'll take a small break. Then we'll go with, after the break, we'll go with the OSPF. Okay. So we'll come back at 9:05. 9:58. So guys, now Ospf. Okay. So now Ospf. So you can close it for now. Okay. Okay. Yes. Done. Okay. So now guys, now we'll go with the Ospf, which is open shortest path first. Open shortest path first. Okay. Open shortest path first. Now let me tell you about this one, some theory, and then we'll go with the practicals also, the configuration. Now Ospf, it's an open standard protocol. Open standard protocol. It comes under the family of link state protocol. It comes under the family of link state protocol. Link state protocol means the updates are sent when the link state changes. That means if the link state is up or down, or if it is coming up from down, it is coming up, then only the information or the update will be sent. Okay. Now the next one. Here the Ospf uses a metric called coast. The metric of Ospf, it is called coast. And coast is calculated by an equation, reference bandwidth divided by interface bandwidth. Reference bandwidth divided by interface bandwidth. This is the equation to calculate the coast. Okay. Now the next thing. Reference bandwidth. Bandwidth. Sorry? Interface bandwidth. Reference bandwidth divided by interface bandwidth. We'll discuss what these things are. Okay. Now here the Ospf uses an algorithm called SPF algorithm, shortest path first algorithm, or it is also called Dijkstra algorithm, Dijkstra, Dijkstra's algorithm. Okay. Now the next thing. So Ospf, so working of Ospf. Okay. So let me tell you the working of Ospf. If two routers here, R1 and R2, R1 and R2, suppose you got two network, R1 is having 10.0.0.0/24 and R2 is having 20.0.0.0/25, or suppose it's 30.0.0.0/25. Okay. Now if you use Ospf, what happens is that the R1 router will start sending, or suppose he will start sending a hello packet. He'll start sending Ospf hello packets.
After every 10 seconds.
Not 10. I really don't remember the time, the hello interval. Of course it need to be 10 or 5, I suppose. 10. Okay, it's 10 on.
4 times 10.
Yes. So hello packets will be sent. Then so this router will be in init state at that time. The router will be in init state at that time. Okay. Now when the hello is reached to router 2 and the router has seen this hello, he will reply back with another hello. So what happens is that he will check certain conditions, or he will check certain values, whether these values or these conditions satisfy or not. If the values or the conditions satisfy, they are gonna send the hello. R2 is gonna send the hello packet to R1 also. Okay. At this time, what happens is that the neighborship is formed. What happens? Neighborship is formed. Okay, so the neighborship is formed here. When neighborship is formed, it will be updated in the neighbor table. Okay, so R1's neighbor table will have R2's information and R2's neighbor table will have R1's information. Clear? So neighbor table updated. And then R1 will move to a state called two-way state. It's called two-way state. That means neighborship has been formed. In the two-way state, you will form, or the routers will form neighborship between each other. Okay. Then the next, then R1 will send the next thing. What they will send is that LSR. Okay, it's not LSR, guys, it's DBD. Okay, database description. Okay, so they will send a brief description of the, say, whatever networks they have. They will send a brief description. They'll send it like this. R1 will send it like this to R2. Hey R2, I know about the 10 dot network. Do you want to know about it or not? Like that, he will send something called DBD. And DBD is called database description. Database description. Okay. Now, so when the DBD is sent, and if R2 doesn't know about the 10 dot network, he's gonna request it. What he's gonna do, he's gonna request it. Hey R1, I do not know about the 10 dot, please send me about the 10 dot network. So that is called link state request, LSR. Link state request. Now, then R1 will send the next value, which is the network value or the network things and all. So that is called LSU. What is it called? LSU, or link state update. Link state update. Okay. Now R2 will now acknowledge back with something called LS acknowledgement. LS acknowledgement. So these are the Ospf messages. Hello message, DBD, LSR, LSU, LS acknowledgement. Okay. So these are the Ospf messages. Now again, so here again you got some more states here. You got init state, and then you got something called xstart state. Then you got something called exchange state. Then you got loading state. And at last you got full state. So these are the Ospf states: init, two-way, xstart, exchange, loading, and okay. Okay. Now guys, let me again tell you. So this full state, that is called adjacency. That is called adjacency. So if two routers are formed to become, or are said to become adjacent when they have gone to the full state, that means whatever they need to share, they have it. It has been shared, and everything have been calculated, and he is in the full state. Okay. Now Ospf, I told you about the neighborship and the neighbor table. Okay, the neighbor table contains the neighbor router's information. Okay, and second table is the topology table. It is the topology table, and the topology, so whatever they send, say this network information, those network information, everything will be there in the topology table. Okay, in Eigrp I told you it consists, the topology table consists of possible route information, but here it is not like that. Here it is just a little bit different. It is here, it is the entire database will be stored in the topology table. It doesn't check whether it is the possible route or not. So the entire database will be, so the LSDB or the link state database will be present in the topology table and will be common to all the routers. Okay, now at last they will find out the best route and place the best route in the routing table. Clear? So this is how Ospf works. Clear? Now that the next thing, Ospf area, Ospf area concept. You can write the heading Ospf area concept. Okay, suppose you got multiple routers here, R1, R2, R3, R4, suppose R5, R6, R7, R8, etc. You don't need to draw it, just for explanation I'm telling it. Okay. Now, suppose R1 here has got a network. Okay, R1 has got a network 10.0.0.0/24. Okay, now suppose the link keeps on flapping in the sense it will come up, again will go down, again will come up, will go down, again up down, like that. It will keep on flapping. Okay, so when it comes up, the router here will send the, say, the update here. So whatever the update or whatever these they are sending is called link state advertisement. What is it called? Link state advertisement. So they will share these link state advertisement, or it is called LSA. So they will share the LSAs. Again, this router will share the LSAs to this router. Again, this router will share the LSAs to R6. And this router will share the LSA to, again, R6. This router will share the LSAs to R3. Again, this router will share the LSA to R7. So the problem is that all the routers, say, they need to run the SPF algorithm. All the routers need to run the SPF algorithm. That is actually a, say, a difficult thing. Okay, that's actually a difficult thing to run the SPF algorithm, that too continuously. Say, that's a difficult thing for the routers. Okay, because say it consumes more resources of the router. Okay, every time when it runs, it will consume more resources of the router. There's no need to run the SPF algorithm like that. So what we will do is that, say, what here we will do is that we will suppose that we are dividing this Ospf into, yes, multiple or smaller area. We will divide it into the smaller area, smaller parts, or each part is called an area. Okay, suppose this area, let it be area 200, and this area, let it be area 400, and this, let it be area 0. So what we have did is we have divided into smaller area. Okay, so now why did we do it? Because to decrease the overload of the router. Now if this link goes down now, then the LSA will be sent to R2, LSA will be sent to R5, and LSA will be sent to R6, and only the 4 routers need to rerun the SPF algorithm. Nobody else, I mean R3, R7, R4, R8, etc. There is no need for them to rerun the SPF algorithm. So we have reserved, or we have, say, not wasted their resources, or we have, say, stopped them from being, stop them from consuming the resources Clear, guys? So there is an area concept in OSPF. We'll have the area concept here. We'll divide the entire OSPF topology into multiple smaller areas, multiple areas, so that it will be easy for them to work. Okay, now this area 0, that is called backbone area. That's called backbone area. So without an area 0, OSPF is not valid. So you need to have an in the OSPF topology, there is a must that you need to have area 0. Okay, and the next, this area, or area 200 and area 400, these areas are called non-backbone area. What is it called? Non-backbone area. So the non-backbone area should be connected to the backbone area, which is area 0. Clear? So this is the area concept in OSPF. Any doubt? Okay. Yes. Do you want to note it down, or shall we go to the next one? Note down. Okay. Yes. Note it down, please.
What about the border router?
Yes. Now you can see here. So R2 or R3 or R7 or R6. These routers, you can see it. Say these R6, he is participating in two area. Area 200 as well as in area 0. So the router participating in two or more area, those routers are called area border router. Those routers are called area border router, or it's also called ABR. ABR. Clear? So ABR is a router which works, or which say runs OSPF in minimum 2 area. Clear? Okay. Now you can write down. Kevin, having doubt? Sure? Okay. Now that we'll go with some more thing. Okay. The next thing is called wildcard mask. Wildcard mask. Okay. You might have heard about, you not that you might have heard, you have heard about subnet mask. Okay. Subnet mask is a value which is used to represent the network bits and the host bits. Wildcard mask also is a similar value. Okay, but you can say, for now you can say the wildcard mask is just opposite to subnet mask. Okay, so in subnet mask, say the network portion is represented using 1 and the host portion is represented using 0. In wildcard mask is just the opposite. That means the host portion will be represented using 1 and the network portion will be represented using 0. Okay, so if at all you want to find out the wildcard mask for a network, suppose 10.20.30.0/24. So what is the subnet mask here?
0.0.0.25.
Subnet mask.
Subnet
255.255.
Yes. So the subnet mask here is 255.255.255.0. So the wildcard mask here will be 0.0.0.255 because /24, that means 24 bits are reserved for network. So 24 zeros will be there and 8 ones will be there. Clear? So if I give you a question, are you able to find out the wildcard mask? Okay. So now, yes, 50.21.51.20/25, 88.48.51.54/30, 82.43.50.0/23, 8 or suppose 7.6.0.0 slash 15, 200.32.0.0 slash. Okay, so guys, just a minute. So this is the network here. Just a small correction here, it is 0. Okay, so now 11 and 32.42.52.0/28 or suppose 64/28. Can you find out the wildcard mask for every question, all the questions? One more small correction here, guys. Okay, here it is not 54, here it is say 52, make it 52. Okay. Yes, now you can do it. Done. I'll wait for everyone to finish. What about online, guys? Done? No need to hurry, guys. Take your time and do it. Pratik and Srikanth, how far you have reached? Last one. Do it. Done. Okay. Now, done. Okay. Now we'll discuss the answers here. What is the answer for this one? The first one.
127.
127. Okay. And guys, again, if at all you want me to do it, then let me know. Okay. Now for slash 30. 0.0.0. 3. It's not 250, it is 3. That means, okay, you might have done the reverse, I suppose you can say here, say you need, or 30 bits will be zeros and the last 2 bits will be 1. Okay, so that means say 0 0 0 0 0 0 0 0 dot, again full 0, again full 0, again the last octet you got how many zeros here? 6 zeros in the last octet. So 1 2 3 4 5 6 and 7 and 8. And what is the value here? 1 plus 2. So the value is 0.0.0.3. The next one.
0.0.1.255.
0.0.1.255. Everyone getting it? Srikanth also got it? No. Simple thing. 23 bits are for reverse. You did the reverse. Okay, so make sure that you do it correctly. Okay, so 23 bits are made zeros and the rest, how many bits? Rest how many bits are there?
7, 8, 9
bits. So the rest 9 bits are made 1. Then you will get 0.0.1.255. And what about the next one?
0.1.255.255.
0.1.255.255. Everyone getting? Okay. Slash 11.
0.31.255.255.
0.31.255.255. So that means the 3 more bits, right? 3 more bits in the second octet will be 0 and the rest 5 bits will become 1, and that will give you 31.255.255 in the second octet. Anyone? 0.0.0.15 or 50. So this is how you will do the, or you will calculate the wildcard mask. Okay. Now shall we do a configuration, Ospf configuration?
Yes, sir.
Okay. So now, so let me take the packet tracer. Usually I will take it in the GNS3, or let me take in the GNS3 itself.
Sir,
Yes.
sir, how many protocols are there in CCNA syllabus?
In
I
C
mean, IGP protocol.
protocol, OSPF. Yes.
And what about the RIP?
RIP and Eigrp is not there, but still I taught you theoretically because there are chances that in the interview they will ask the question.
Okay, so Eigrp, OSPF and
Only OSPF is there. OSPF and static. Static is not a protocol, but still static is a type of routing. But static is also there.
okay. And is there any BGP portion?
BGP portion is not there at all.
Okay, got it.
Yes. Okay. So previously we used to have, in previous CCNA syllabus, we used to have RIP, Eigrp and OSPF, and also a small portion of BGP, but they have removed all these things. Okay. Just give me a moment. still. So let me try to take it, guys. If at all we are having any errors, we will be opening it in the other one. Okay, Ospf basic. Okay, maybe later we'll take, because I don't think that the GNS, my GNS is having some issues. So maybe we'll take it tomorrow. Okay, take it tomorrow means in the GNS3 we'll do it tomorrow. Now that, let me show it how to do it, and we'll do it in the packet tracer. Okay, so now again let me take the packet tracer here, Cisco. Now suppose let me take two routers. Okay, let me take two routers. Okay, and say let us implement the same old topology that we have done yesterday. Okay, with the two routers. So now again, say let me insert the serial cable and all. So the serial connection, let me zoom in and say turn it off and insert the serial, and again turn it back on. The same thing here. I hope you can see this right. Now suppose again, just give me a minute while I'll do the configuration. Say here, where is this one? The usual network. Yesterday's network itself. So here we got, okay, again it's gone. So this LAN, this is 10.0.0.0/24, and this is 30.0.0.0/25, and this is 20.0.0.0/30 network. Okay, so now notepad, I ought to save that yesterday but I didn't. Okay, so interface, or n, say en interface gig 0/0/0, and the IP address, here it is 10.0.0.1 255.255.255.0, and no shit, and again exit, then interface serial 0/1/0, IP address 20.0.0.1 255.255.255.252, no shit. Now here also serial 0/1/0. Okay, so now this is 30.0.0.1/25, so it's 128. Then this is 20.0.0.2. Now this computer 10.0.0.2 255. So it is 255.255.255. say 0. Okay, and 10.0.0.1, and the same thing will be configured. The IP will be configured in this computer as well. One to it. Okay, and 30.0.0.1. So now let me just save it, so that each and every time I don't need to do it. Basic. Okay, now so here Now that when you check the routing table of the router, okay, so to see the routing table, what is the command? IP route, or the command is do show or show IP route or do show IP route. So when you check it, you can see the R1 has got two directly connected networks, which are 10.0.0.0/24 and 20.0.0.0/30. It doesn't know about the 30 dot network. Okay, now the same here, when you take a look at this router, it doesn't know about the 10 dot network. Do show IP route. It doesn't know about the 10 dot network. It only knows about this 20. So it doesn't know about the 10 network. It knows about the 30 dot network and the 20 dot network. Everything fine? Now we are going to do the OSPF. So we'll do the OSPF like this. We'll go to the router. We'll mention the command like this: router OSPF. Router OSPF. Then we'll give a number here. So this number is called process ID. This number is called process ID. So you can see this process ID here. You can give any number from 1 to 65,535. You can give any number. Okay, suppose that I am giving 100 here. I'm giving 100. Then you can see you have moved into the OSPF now. So router OSPF 100, when you give it, you have moved into the OSPF config-router prompt. Then you will mention here what you actually do is that you will mention the directly connected network. So the directly connected network is 10 dot network and 20 dot network will be mentioned. So in static we mentioned the unknown network. In dynamic routing we will mention the known network, so that these networks will be advertised to the other router. Clear? So we'll mention the known network. What is the known network here, guys, for the router 1? Which are the known networks? 10.0.0.0/24 and 20.0.0.0/30, which are the directly connected networks. So you will mention the command like this: network. The keyword is network. Once you go inside the OSPF, you will mention the keyword network, then the network address 10.0.0.0, okay, /24. But now instead of giving the 24 or the subnet mask, here we will give the wildcard mask. We'll give what? We'll give the wildcard mask. So for /24, so for /24, what is the wildcard mask? 0.0.0. Getting it, Kevin? Okay. Okay, so it is 0.0.0.255. So here we have mentioned the network keyword, then the network address, then the wildcard mask, then we'll mention the keyword called area. We'll mention the keyword called area. Suppose everything is in area 0. The entire thing is in area 0. Then what we will do is that we'll mention area, then the area ID is 0. Clear? This is how you will give the command in OSPF. Okay. Now again, one more thing. Again, network space, then the next network address. Which is the next network address? Say yes, 20 dot, not this router, this one. Say 20.0.0.0/30. So here we'll mention the command network 20.0.0.0. For /30, what is the wildcard mask? 0.0.0.3. Because say in the figure, I mean in the question that I just given you before, I've just made you do for /30. Okay, so 0.0.0.3. Srikanth. Okay, then we'll mention area ID, which is 0. What happens is that if you mention this, then they will start sending the hello packets. They'll start sending the hello packets, and again, if you configure this router, then they will become the neighbors. They'll create the adjacency as well. Clear? So now we'll go to this router. And this router, I told you, you got again 2 more networks. The second router has got 2 networks, 20 dot network and 30 dot network. So what you're going to do is, you will go to the config mode, you will mention the command like this: router OSPF. You can give any value from 1 to 65,535. You can give any value, 100, 200, 300, any value you can give. Suppose I'm giving 200. Okay, then you can see I moved into the OSPF prompt. Okay, where I'll be giving the command network space, then the directly connected network. Here it is 30.0.0.0/25. So then command is 30.0.0.0 for /25. What is the wildcard mask? 0.0.0.127. Okay, and then Srikanth is getting right. Okay, and then we'll mention the area ID, which is area 0. Okay, then we'll mention the next network 20.0.0.0.0.003 and area 0. Clear, guys? Now when you mention this, later you will see a message. You can see something. Ospf adjacency. Process 200. The process 200, Ospf process 200 has formed a neighbor, and they are moved from loading to full state. That means they have formed the adjacency. The routers have formed the adjacency. So what happened was, see, the router here, they send the hello packets to each other. They send the hello packets to each other, and I told you the process there, what happens. And they have shared the LSR, they have shared the LSA, say the LS update, like that. Okay, at last they have sent the LS acknowledgement also, and finally forming the adjacency. Clear? So now if you take a look at this router, you need to have, say, to take a look at the router's routing table. Show IP root. You can see 30 dot network in R1. Did you see that? You can see the 30 dot network, and in 30 dot network 30.0.0.0/25, how did he get it? Via O. O means Ospf. O is Ospf. Clear? So via Ospf he has got the 30 dot network. So this 110 is the AD value, and this is the metric value. Clear? Okay. Now here when you check the same thing here, do show or show IP root, you can see it has obtained the 10 dot network from Ospf O here. Clear? And again you can see 110/65, where 110 is the AD value, administrative distance, and 65, that is the metric value.
How will calculate the metric value?
Yes, that's what we are coming. Now I told you the metric value, they'll calculate the metric value, they'll calculate the metric value by using an equation. And what was the equation? What is the equation, guys?
Some bandwidth.
It's not some bandwidth.
Reference bandwidth with interface.
Yes. Reference bandwidth divided by interface bandwidth. So now let me tell you. Okay. So here, so the reference bandwidth is a constant value. The value is always 100. The value is always 100. Okay. Now the interface bandwidth is the bandwidth at the respective interfaces. Okay. Now suppose here
Reference bandwidth is 100 for Ospf or other?
for Ospf. Only for Ospf. So here you can see, here it is gigabit Ethernet, right? The router uses gigabit Ethernet, and the switch uses fast Ethernet. So what happens is that they will work in fast Ethernet speed, or the bandwidth of the fast Ethernet, because the gigabit Ethernet is able to work in 1 Gbps, but the switch interface will not support it. So they will come to, or they'll work in 100 Mbps. So here when you take a look at here, okay, so for R1 to go to this 10.0.0.0/24 network, the cost here equals the reference bandwidth, which is a constant, which is 100 divided by 100, which is the interface bandwidth. Okay, so the cost here will be 1. So here the cost will be 1. Getting it? Now here the cost. So the cost will be calculated by the equation reference bandwidth divided by interface bandwidth. Reference bandwidth is always a constant 100. Interface bandwidth for serial interface, I have told you the serial interface, the base bandwidth is 1.544 Mbps. So yes, 1.544. So 100 divided by 1.544 will give you around 64 something. Okay, so the cost here is 64.
Plus 1, 65.
Yes, I'll tell you. Now again, so here also the cost is 1. Okay, because they use the say 100 Mbps is the bandwidth there. Okay, and when you go with the equation, you will get 100 by 100, which is 1. Clear? So they have calculated the interface or interface cost they have calculated. Now R1 will send the network information to R2. R1 will send, hey R2, I know a 10 dot network, for me the cost is 1. Then R2 will calculate the cost. For R1 to reach the 10 dot network, the cost is 1. For me, being R2, to reach this 10 dot network, I have to add this cost also. Getting it? So R2 need to first get to R1. After getting to R1, then he can send the packet to 10 dot. So they will add this 64 plus 1 and they'll get this 65. So when you take a look at this router neighbor say routing table, the cost is 65.
There is some maximum limit for metric value.
There's maximum.
Limit.
Yes, of course there is some limit, but that's a higher value or something. Okay. Now again, so here the same thing happens here. The metric value, it is 1 here, and here the metric value is 64. Now the router R1 will calculate the metric by adding 64 plus 1. That is how he will get 65. For R1 to go to 30 dot network, he has got a metric of 65. Clear? Everyone? Okay. So when you take a look at R1, you can see this is how you got 65 here. Clear? Okay. So this is how they will calculate the cost. Any doubts?
No.
Okay. Now to view the neighbor table, you can have the command, or you can execute the command show IP ospf neighbor. The command is show IP ospf neighbor to view the neighbor table. So if I view it, show IP ospf neighbor, you can see yes, the neighbor, it is, you got another neighbor which is R2. Okay, and the neighborship has become full state. Clear? Now sorry guys, again when you take a look at the neighbor table here, show IP route, you can see, sorry, not show IP route, show IP ospf neighbor, show IP ospf neighbor. Again you got another router here, so this is R1 router. Okay, so I told you in R2, when you take a look at the R2's neighbor table, you can see R1's information. Then see the state is also full, that means they form the adjacency. Okay. Now to view the topology table, which you will not understand now, but still show IP ospf database is the command to view the topology table. You won't understand, but just go with the command for now. Okay, and of course you know the routing table, show IP route. Clear? Now to view the OSPF interfaces, you have the command show IP OSPF interface. Show IP OSPF interface. Now okay, so interface, you can see the interface details. So this router participates, so OSPF participates in gig 0 or OSPF is enabled in gig 0/0/0. Okay, and the cost is for gig 0/0, the cost is 1. So here I told you the cost is 1 here. The cost is 1. Okay, and here the cost is 64 for the serial interface. Let me again show it to you. The cost is 1 in gigabit Ethernet 0/0, and for say yes, for serial 0/1/0, the cost is 64. Clear? So these are the relevant things here. Any doubt? Yes or no? Yes.
Actually, we can understand it, but we have to practice it.
Yes, of course you can practice. Okay. So today's task, practice this thing. Okay, OSPF. And yesterday I have given you the homework, right? With the 3 routers. Practice the OSPF in those 3 routers with the area 0.
3 and 5 hours.
Actually, the configuration itself, I have some doubts.
Of course, you can ask the doubts, no issues.
After class.
Okay. Now, not the 5 routers config. Say you can do with the 5 routers also. Once you are okay with the basic routers, the basic the 2 routers and 3 routers, then you can go for the 5 router thing. Clear? Any doubts or anything from your part? No. Online guys, anyone? I suppose everything is fine. Okay, now let me stop recording and